Thunder Horse platform. It's about $1 billion that BP and I believe Exxon partnered together to build this, and it's a floating platform. It's one like that had exploded and caused a large leak last spring. So these things are very precarious, and if we're thinking that oil production is going to be easier in the future, we're probably a little bit delusional and fooling ourselves. This is probably just a sign of the future, and I think the oil spill as well. Price of oil has gone up tremendously. Historically, it's around $20 a barrel, through the 1980s, with fluctuations up to $40 a barrel. In the 90s, it got down to like $15 a barrel. We're buying gas for $1 a gallon, or less than $1 a gallon if you lived in Georgia. Now it's $3. We're probably getting close to $3.50 here shortly. So, and there's a whole field of geologists and other scientists that have been looking at this idea about peak oil. The Association for the Study of Peak Oil, it's started by, I think the guy he's Scottish or Irish. Colin Campbell is his name. He heads up this organization. He's a former geologist, worked in the oil industry, so he's quite knowledgeable on oil production and discovering oil and producing oil. And this is his graph. Let's see if I can zoom back in. Again. Zoom a little more here. Well, there's no way to make that bigger. Let's go back. Well, what we see here, the red bars are the rate of discovery of oil. This is in GB is gigabarrels, so billions of barrels of oil. Here we can see the peak of discovery was in the late 1960s, right here, at just under 60 billion barrels discovered. And then the black line shows our historical production of that. This is internationally now. Up through, there's our peak in the 1970s, and then we surpassed that peak a second time in the 90s. And here we are. This graph's a few years old now. Need to update it. Kind of the rule of thumb is that it takes about 40 years. If you look at other countries that have had peak production, peak discovery and peak production, there's roughly about a 40-year lag period between the peak in discovery and the peak in production. So if you project forward that 1960 discovery production, then we're looking at a peak in production globally in about 2010, which we just passed. And actually, we have an economic decline right now, recession, I guess. And oil production has peaked in about 2008 or I think 2008. We'll see if the economic recovery, if it occurs, what's going to happen with oil production. It may or may not come back. And here's their website, peakoil.ie. I think that's Irish website. Just the same data, but breaking out into different kinds of categories of different kinds of crude oil. They're predicting the peak about 2010. So some people call this a bumpy plateau. This area. Up here at the top, it's not going to be a steep decline, but there'll be maybe a decade of where it goes up and down around a mean value. But eventually, it's going to go down and down. All right, so that's one of the concerns about energy. Of course, this is a concern that says, well, we don't have enough carbon. And there's going to be a problem in the future with at least with the oil. And some people argue that the coal and natural gas are probably not too far behind this. There's not much, not as good a data on the coal supply as there is on the oil, and natural gas a little better, but not as good. The flip side is climate change, and I thought I'd just give a quick overview. So. It's such a main driver of why we're concerned with green buildings and trying to make them so they produce less greenhouse gases, is just go over some of the basic science here of really what's going on in the atmosphere and what is the greenhouse effect. So if we have here's what we have, our atmosphere, and then we have our Earth surface down here. Sun's coming in at the top. Solar radiation average is about 235 watts per square meter. That's on a annual average for the Earth. It doesn't vary too much from throughout the year. Of course, it varies depending on where you are on the Earth, how much you're receiving at any 1 square meter. But if you take the Earth as an average, it's about 235. So out of that, 168 here makes its way through the atmosphere. Some of this is reflected directly or is absorbed into the atmosphere here, and will be re-radiated out as thermal radiation. So we're going to be talking about, when we talk about heat transfer with buildings, making a distinction between solar radiation, which is at short wave. It's on the average, the 400 to about 1100 up to maybe 2000 nanometer wavelengths is our visible and near infrared, which is mostly the solar radiation. But then anything that has a temperature, including you as a person, or the chair you're sitting in, or the wall that's next to you, has a temperature, and anything that has a temperature is going to radiate thermal energy. So the Earth, by having a temperature that's roughly about 300 Kelvin, that's scale, is going to radiate energy. And here we can see that it has to balance. This 195 plus the 40 should give us back our 235. So on average, over a short period of time, these have to balance. But here we see the greenhouse effect down here. Of course, our greenhouse gases are absorbing a significant amount that's being re-radiated back to the Earth. So the solar energy is able to get through the atmosphere, a large majority of it, bypass the carbon dioxide and the water vapor. But then when it changes wavelength due to this absorption and re-radiation, it's going to be trapped by these greenhouse gases, and the main ones being carbon dioxide, methane, water vapor, and then some of the other minor components would be like carbon monoxide, ozone. And the next slide will show us that. So this whole greenhouse effect is basically the thing here is it being recycled. So this energy gets trapped by the clouds and the gases, re-radiates back to us here. And let's see, go to the next slide. Yeah. So this is giving you the radiation that's transmitted by the atmosphere. So here the distinction between the red and the blue. The red is the solar radiation, again short wave. Here's ultraviolet, right? Very short wavelength. Anything less than 400 down to about 100 nanometers before you get to X-rays is ultraviolet. Stuff that colors your skin or gives you cancer if you get too much of it, skin cancer. Visible light here, or red, orange, green, yellow, blue, is where the peak of solar energy is. And then past that, you get into the infrared. And scientists call this the near infrared, which is close to basically the right here at this line, this intersection between visible and infrared would be called, is where the red light is. So the next to that is the near infrared. And then further out, you get into the long wave radiation, which again, some people call it thermal radiation. So the energy is being absorbed by things in the atmosphere. So here we see a graph of the different components of the major components absorbing radiation across these wavelengths. So here it's in microns, so that's a millionth of a meter. This would be 1 micron is 1,000 nanometers. So visible is 400 to 700 nanometers, right? So that would project down to 0.4 to 0.7. It's on a log scale. And here's our main gases that are absorbing: carbon dioxide, oxygen, it's actually a greenhouse gas, ozone, methane's another large one, nitrous oxide, N2O, and then some just what's called Rayleigh scattering. But then the other big one that you don't hear as much about is water vapor itself is actually a major greenhouse gas. It's much more variable, and there's much more mixing of the water vapor due to clouds and heating of the troposphere. But you add all those up, and then you get the total absorption, and you can start to see the basically where energy is absorbed. 100% is out here. So basically, energy that's at a temperature that would radiate at this wavelength is basically captured almost 100% by the atmosphere. Same thing over in this area, but we had this one gap where a lot of things are able to get out. Now you're down to maybe 10% or less is absorbed, so that means 90% of it escapes, and that's what's escaping from the Earth. So if you're able to take your thermal camera up to a satellite, if you're sitting on the moon and took a shot of the Earth, you would see a good image of the Earth if your thermal imager was in this infrared band. And of course, the sun is much higher temperature. It's at 5,000 Kelvin, 5,500 here. So it's radiating at a much shorter wavelength. By being at a cooler temperature here, 200 to 300 Kelvin, the Earth is re-radiating it at a longer wavelength. So basically, the cooler you are, the longer your wavelength, the shorter, then the higher, or the higher the temperature, the shorter the wavelength. So if you're really extremely high, you'd be radiating at X-ray and ultraviolet. Okay. Doing on time. So what's some of the evidence? I thought I'd just put together some of the things. This is mostly stuff that's available from the group that does the climate modeling, which I can't think of their acronym at the second here. The IPCC, yeah. Intergovernmental Panel on Climate Change, IPCC. They're the ones that collect a lot of the data and put up all the reports on the status of climate change. The longest history, we have a direct measurement of carbon dioxide, which again is one of the main greenhouse gases that we've been affecting by using fossil fuels, is at the Mauna Loa Observatory in Hawaii. And you can see here, going back to the late 1950s, and it has this very characteristic sawtooth pattern that's seeing the increase go from about 310 parts per million in the beginning to over 380 today. We're probably approaching 390 as we speak. And this sawtooth is the difference in basically the photosynthesis and respiration that's occurring between the northern hemisphere and the southern hemisphere. The northern hemisphere has a lot more land mass than the southern hemisphere. The southern hemisphere is kind of our ocean hemisphere. So due to the difference between the rate of photosynthesis and respiration, you get this basically oscillation each year. Northern hemisphere is going to be able to take up more of that CO2 in the summertime when it's growing, so this is going to come down. But then in the wintertime, it's going to have more respiration. It's going to release a lot more of that CO2 and doesn't have the ability to absorb as much of the CO2 as you would see here. So, of course, that's been going up. Very strong evidence, direct measurement. And then, what's the effect of that? Here's a nice record of the century-long change in temperature of the ocean, which is in blue.